Was it about 47 through 49?
The wording of it maybe, or
Because it seemed to me, I thought we talked about this when we were doing the, and maybe it's just the wording of it, okay? So like on 47, suppose that the line y equal 2 is a horizontal asymptote. So we've got y equals 2 right here of some function f. So then if you had the g function, so if g was equal to f plus 3, what does that mean? So if we had some graph that came down like this, these were some of those graphs we were kind of looking at yesterday. You know, let's say we had a graph like this. And then we were going to take that graph and shift it up 3. What would happen? All the points would go up 3, right? So now the horizontal asymptote would be where? Up 3, right? Which would be at 5. So it'd be y equals 5. So on part A, explain why line y equals 5 is a horizontal asymptote, because this graph would shift up 3. Does that make sense? So think of it this way. Remember when we traced? Remember we had, I think, who was doing it? Tim was doing it? He traced out at 1,000, right? So on this one, if you traced out at 1,000, you get like 2.0001, right? Well, if you shift that up 3, now you're going to get 5.0001. Right? So then on 48, it says, what would be the horizontal asymptote if you shifted this graph left 1? So if you took this graph and shifted it left 1, what would be the horizontal asymptote? Still be y equals 2, because it would just be over here, but it would still be y equals 2. And then C, now what do we do with something like that? So where do we start with something like that? Now this one a little trickier for sure. It depends on what asymptote you're talking about. Let's talk about just moving this graph first. Where do you start? Like if you were going to redraw the new graph, where would you start? Start on the inside. So you'd want to shift left 4. And the only reason I say not do the +1 first is because of this 3, right? If the 3 wasn't here, then you could go left and then up, or you could go up and then left and be the same thing. But it's kind of like order of operations. Like if I was going to plug a number in for x, where would I start? Start on the inside. So if I shifted this left 4, okay, now what would be my horizontal asymptote? Still be 2, right? That wouldn't change anything. But what's this 3 do? Stretches it, right? But now, so we got to think about, what does a stretch do? What does a stretch do? I mean, we talked about a stretch, but remember when we were drawing, we had that like weird shaped graph yesterday, you know, in yesterday's homework, and we had to stretch it by 3. What did it really do? It took the y values and made them 3 times as much, right? Well, so what that means is these y values on this graph right here are what? Way out here. They're like 2.00001. What happens if you times that by 3? 6.00001, right? And these numbers down here would be like 1.99999999, right? Take that times 3. What would 1.999999 times 3 be? No. Almost 6. In other words, think of it. I know you're like, well, I can't do that in my head. Well, you don't have to be exact. What you're saying is, if you're saying 1.99999, you're saying a little under 2. If you times that by 3, you're going to be a little under 6, right? Little under 6. So where is our horizontal asymptote at? At 6, right? Because these numbers are going to be a little bigger than 6, and so this stretch, I mean, these numbers will go down here more. These numbers will stretch up, right? Because remember, at 0, it doesn't stretch. It stretches this way. So these are going to go up by 3. These are all going to stretch up by 3, right? And so that asymptote's going to be at 6 now. Then we do the +1. So y equals 7, right? So y equals 7. So the whole thing goes up. So y equals 7. All right, and then 48. So, I mean, now, so I take it back. I was a little hard on you when you asked about 47 through 49. I was like, geez, what are you, stupid? I mean, it's not what I didn't mean that. But I'm just surprised that was our first question. I thought maybe there was something else. But no, this is good. I mean, I think we would have talked about this even if you hadn't asked about it. I think I would have said, well, what about these? Okay. Now we got a vertical asymptote at -3. So maybe it looks like this. Comes down here. I mean, maybe, who knows? Doesn't matter, but that'd be an example of a vertical asymptote at -3. So what happens if you shift this graph up 3? The vertical asymptote wouldn't change, right? All those points, and it would still be approaching that. Okay, then what if we shift it left 1? It'd be at x equals -4, right? And then if we do this same thing again here, starting on the inside, so we shift left 4. That'd be at -7. Then we're going to stretch these by a 3 factor. What's that going to do? That won't do anything, will it? These values will just stretch up. These will stretch down, right? If it's getting really close to 0, think about this. If this was getting really, really close to 0, we don't know that, they didn't tell us that, but if it was, and you stretch it by 3, what's really, really close to 0 and times by 3? Really, really close to 0, right? I mean, 0.000000001 times 3 would be 0.0000003, right? I mean, it's really close to 0, right? So times by 3, as you get close to 0, it doesn't do anything, really. Right? It just makes it really, really still close to 0. So anyway, that wouldn't do anything. So where are we at? -7? And then we shift up 1. What would that do? Nothing. So x equals -7. All right, and then 49. Okay, so now this is a little different scenario. Now you did have a calculator. So if I was going to ask you this on the quiz, I would say, go ahead. We should get the calculator. Just as part of our review for the quiz, this would be a good one to talk about our calculator. Will, you're the presenter. Yeah. Weren't you the presenter before? Yeah, that's okay. You were so good last time.
It's not letting me down.
It's not? Keep trying. But you gotta have the hat on to log in. If you don't have the hat on, it's not gonna let you log in. Because you're not connected to the... All right. So let's go into a graph stream. So let's say this was on the quiz and I give you these functions and then I'm going to ask you some domain and range and, even, odd, and, I could ask you all kinds of things. So you need to be up now. Okay, you're on F3. Now I don't care if you're on F3, right? But arrow up. Do you have something on F2 or F1 or? Yeah. Do you want to keep those for any reason or? Okay. Yeah, it's fine. It doesn't matter. I'm just saying, whenever it pops up F3 or F2, then I'm thinking, I probably have some others. Now, notice, go back to F2. Why don't you delete, or just hit clear is a good thing. Control, delete, just clear. Okay, and then arrow up. Now, if you do have some graphs you'd want to keep, you can, and about the only way is with your thumb or your finger on the trackpad is you can check and uncheck this box. So like if you had 2 or 3 graphs, but you didn't want them all to graph at the same time, but you didn't want to erase them, you could go in and uncheck them. And then now as soon as you start typing, this is going to check, that box will check. So let's go ahead and put this fraction in here, okay? So, and so we got x minus, what is it? X minus 3 over x squared minus 9. And hit enter. And then hit tab again. And then go to F2. Why is it that? Oh, you know, that was on there. When you cleared it and then did the up arrow, it didn't clear. You have to hit enter, I think, to actually make it go away, I think is why it didn't disappear. And now let's do the other one, which is 1 over x plus 3. So everybody needs to be able to do this on your calculator, okay? On the quiz tomorrow, right, we're all going to be ready to go, right, for this quiz. If I'll be here after school if you've got concerns and things we're talking about. You have some time, work time today. I'm going to give you some trig stuff to do. But your first priority will be, you know, just kind of review for the quiz and stuff like that. All right, so you got a red and a blue, and, you know, if you want to move these around, you can, with your thumb, I mean, it's not probably worth it, because it's not that easy. It's a lot easier for me with my calculator, but like on the trackpad, you could go, why don't you do that real quickly, just show. So now see how that gets to, see that little hand? Okay, and now it says label, but when you get that little hand, I think you can hit enter. I wonder why you're not.
Oh, your cursor is.
It should be a right arrow.
Yeah, hit tab and get rid of this. Just hit the tab button. Now arrow over on top of that. There you go. What'd you do? Did you hit enter?
No, I just,
Click. There you go. There you go. Get that 4-way. There you go. And now you can. And now I think if you hit Control and then move with your trackpad, it'll move it. Maybe not. Or maybe you have to click the middle of the trackpad.
no, it just pulls it back.
Where'd that come from?
I had the scratch pad.
Oh, now, okay, I didn't notice this. You're in a document right now. Okay, so let's talk about that a minute, which is fine. Doesn't matter. But if you go to home, go to the home screen. And when your calculator, a lot of times when it first comes up, if you do new document, I'm sure you guys have all seen this. So if you do new document, right? Now it's going to ask you if you want to do changes. Let's say no. Okay, and so a lot of you have seen this, and so you said, oh, I want a calculator, I'm going to do this. Now, I'll be honest, I never do this. I don't like working in the documents, because unless you're going to save it, there's no reason to be in the document screen, right? So where I typically go is always a scratch pad. So even if I got that on my screen, I'm just going to hit escape. I'm going to go to my scratch pad and do all my graphs on the scratch pad. But if you want to be in a document, that's fine. It doesn't matter. I mean, I think it's the same. You know, there are some reasons why you might want to be in one or the other, but I think for the most part it doesn't matter. Okay, so now if we go tab, of course now we didn't say that. So go hit tab and let's go up. Oh, okay, now I've seen this happen to people before too. This is good. Now, here would be an example, maybe, here would be an example of a question I might answer for you on the quiz. You know, I've said I'm not going to really be much help at all in the quizzes. And later on, you've got to understand how your calculators work and stuff, so I'm not going to be much help. But here early, probably, if you got this and you were going to grab something, this came up, and you don't know what to do, come up and ask, and I'll help you. If you go to Menu and Graph Entry, okay, there are different types of graphs. We want to be in function. Somehow he got in relation. So I don't remember how he might have done that, but that's why. So now arrow back up. There you go. Now clear that out. Okay, so here we go. So let's put that fraction back in. But this is good because one of the things, like I said, you have to be able to do in the quiz tomorrow is get on your calculator, do a graph, set a window. Now he's already got -10 to 10. that way. I talked to you guys about that Zoom standard, right? If you go under window, if you go menu 4-5, you'll get, okay, what was it, X plus 3? Okay. Now, if you go menu 4-5, that's a nice one to remember. Menu 4-5 is just a standard window, right? Menu 4-5, and you go 10 to 10, you go 6, negative 6 to 6. That's a nice square window. Okay, the heck with moving that stuff around. It's in the way, you know, it's more of a pain than it's worth. Okay, now notice they look the same, right? That's the point of this. They look like the same exact graph, but they're not. They're not. And so, but let's go ahead and let's just answer the question. So it says, show that f of x is equal to g of x for all x such that x is not equal to plus or minus 3. Okay, what does it say, plus or minus? Yeah. Well, how would you show that? Well, think of your algebra here. What would you do with this one?
X plus 3 times x plus.
Take the bottom, factor it, right? Cancel, and you get this, right? So we just showed that these, right there, that work is your show. That work is your show. Okay? Show that those two are equal. Now, it says except for x being plus or minus 3. Now, I'm not sure I agree with the minus or the plus 3. Well, no, I do too. Because let's put in a 3. Put in a 3 into this first one. What do you get? Undefined. 0 divided by 0. Now, we're going to learn later on that 0 divided by 0 is a special kind of undefined. Okay? Well, isn't that the one I put in Siri? I tried that day. What is 0 divided by 0? Why am I not getting any voice on Siri? Or later, somebody that knows about phones can help me on that. All right, so we get 0 divided by 0. Okay, now, put in 3 into this one. You get 1/6. Oh, so that one 3 works, this one 3 doesn't work, right? Okay, what about negative 3? Put negative 3 in this one, what do you get? Well, put it down here, it'd be easier. You get negative 6 on top, right? And you get 0 times negative 6, which is 0. So you get negative 6 divided by 0. Also undefined. It's a different kind of undefined, though, than 0 divided by 0, which we'll look on the graph here in a minute. Now put negative 3 over here. What do you get? Undefined. 1 divided by 0. So you get undefined for both of them, right, on negative 3. Okay? But a different kind of undefined on that other one. But we can't say they're equal when they're undefined. So that's why it says they're the same. They give the same exact output except at 3 and negative 3, where they're, f is undefined at both of them. G is only undefined at negative 3. Well, let's go to the graph and let's trace it those. Okay? So trace first at 3. So 5, 1, okay, and I'll type in a 3. Now, notice what happens there. On the blue graph, it's undefined. That's the one we said. There's a hole there. So this graph, if I was going to draw it myself by hand, what I've got is a vertical asymptote here. It comes down like this, and right here at 3, I've got a hole. So that's what this graph is doing right here. Now we can't see it, but that's actually what's going on. This is what I mean by two different types of undefined. 0 divided by 0 is typically a hole in the graph, whereas a number divided by 0 is a vertical asymptote. Something we'll investigate later on in a later chapter. Okay, so you don't have to worry about that or know that, but just understand if I ask you to trace or do something, because I want you to use your calculator, you'll be able to answer this question. All right, and then of course, if you put a 3 into the red one, how would we put a 3 into the red one? Hit, let's see, I'm not sure, hit the up arrow. Is it down, up or down arrow? Either one doesn't matter. Up or down arrow where your trace will take you back and forth between the two different graphs. Well, look at this one. When you put a 3 into the red graph, you get 1/6. Okay, you actually get a point. Well, that's where the hole is. That's where the hole is in the blue graph. Okay, in the red graph, we actually get a point. Now, of course, if you put in negative 3, put in negative 3, well, and that's going to be a problem on both of them. That's going to be a problem on both of them. That's undefined. And hit the down arrow. And put in negative 3, and then Yeah, see, that's a problem, both of vertical asymptote. Okay, but so anyway, so just give you a little bit of being able to trace around and look at graphs and stuff. And then, so what's the domain and range of f? Okay, so looking at this picture, what is the domain? Well, we've kind of figured that out. What numbers don't work?
-3 to 3.
-3 and 3 don't work. So everything but those works. Now, I think the best way to do that is just say x can't equal plus or minus 3. Now, you could say -infinity to -3, then -3 to 3, then 3 to infinity, and don't include any of those, right? Put parentheses on all those. So -infinity, of course, you can't include that, right? We talked about that. Don't include infinity. -infinity to -3, -3 to 3, 3 to infinity, if you want to write all that out. But if it's just two values that don't work, just say x is not equal. Can't be plus or minus 3. Okay, so it's what you're saying is it's everything else. It's everything else. Okay, what's the range? What are the y values? Everything but 0. So if you just said y can't equal 0, I'd be okay with that, but you could also say -infinity to 0, and then 0 to infinity. So it's everything but 0. Okay, so it comes up here, and then it goes up there, but it will never be 0 because that's a horizontal asymptote. Okay, and then what about the red graph? What's the only difference?
Doesn't have a bullet.
It doesn't have a hole at 3, so it can't be -3. But it's okay to be 3. So it can't be -3, and again, the range won't be 0. Okay, anything but 0. How are they related? Well, they're the same. I mean, again, that's what we saw. They're the same, except the blue graph has a hole at 3. The red graph doesn't. But otherwise, they are the same. Okay. Does the graph of f have a horizontal asymptote? Yes. What is it? Y equals 0. Remember, horizontal lines are y equals, vertical lines are x equals. So it has a horizontal line asymptote at y equals 0, and it has a vertical asymptote at x equals -3. Okay, so understand, so basically the idea is that you understand enough about rational functions and asymptotes, just enough that when you graph them, you can see it on a graph, you can set a proper window, you can look at the equation, kind of tell what's going on, just stuff like that. Be able to answer your question. Okay? All right. And that's true if it's a trig equation, or it's an exponential equation, or it's a log equation, any of those, based on those pictures that we drew in our notes yesterday. All right, what else? For which one? 18. Down towards the end. Okay, so we have sine 2 pi x. Okay, oh, that's why you had that on there. I got you. Okay, put that back on there. So let's clear these out. Now, without going to your calculator, and my hope would be eventually here, so go ahead and put that in here, but my hope would be that we'd be able to say, okay, sine 2 pi x, we would know something about that. Now, what's that 2 pi do? Changes a period. Now, it is a shrink, right? It's a horizontal shrink, but we know with sine, we used to say, well, the period's 2 pi. Remember how you do that? You divide it like that. So the period is now 1. So my hope, and I'm going to give you an IXL that is part of what I want you to do for homework, to review this stuff, that if the period's 1, you understand enough about the sine graph that it's going to come up here. Divide this into 4 parts. That'd be 1/4. This would be 1/2. This would be 3/4. Because that's the same thing you do with the normal sine graph is 2 pi, pi halves, 3 pi. You divide it in 4 parts. It's going to hit a peak at the first part, going to come down to there, going to hit a bottom there, and going to come to there. That's going to be 1 period. Right? That's what the sine graph is going to look like. So without even graphing on a calculator, I think we need to get to the point where we can just do that. Now, when I say that, I'm saying, hey, this quiz is going to be all calculator, right? But if there was a no calculator part, I want you to know this. The next quiz may have a no calculator part, and this may come up, right? The rest of the year, this kind of stuff may come up in a no calculator part. So we'll try to keep reviewing it and hitting on it whenever we can. All right, but let's look at it. So if we do have our calculator, so we got this. So it's probably kind of a crazy window. It doesn't really tell us to look at it on any interval, really. Well, yeah, it does. In E, it says 0 to 3, right? We're in the interval. So really, here's a good thing to do. So now go to your window. So it gave me the interval 0 to 3. So let's go to window. let's go to this Windows settings, and let's set our X to 0 to 3. Now, what would be a good Y for the sine graph? I would say -2 to 2. -1 to 1 would be fine, but it'd fill the screen. I always like to have a little empty space. So -2 to 2 would be pretty good. And then you're going to get a nice picture of the sine graph in that window. But see, because I know the sine graph goes from -1 to 1, so I was able to set a nice window, right? Because I know that about sine graph. All right, so then it says, where is f increasing? Well, another thing that would be good that you could trace, right? You could trace, but where did we say this peak was? That was at 1/4. And why? Because we know that this is 1. Now you could trace, but you could save yourself a little bit of time if you know enough about the sine graph to know the period's 1. So you know this is 1/2, you know this is going to be at 3/4, right? And so forth. So where's it increasing? From 0 to 1/4, from 3/4 to, what's that going to be? 1 1/4. Remember, this is going to be 2 here. This is 3 over here. So 3/4 to 1 1/4. So that'd be 5/4, right? And then from, what would this be? 1 3/4, which would be 7/4. You can put 1 3/4. You can put decimals. I don't care. 7/4 to 9/4. And then finally at the end here, this would be what? 2 3/4. 11/4 to 3. Right? Does that make sense? So where's it increasing? That just means where's the graph going up? Well, that's some of the terminology we've been using, right? Increasing, decreasing, stuff like that. Okay? Are there any local max or min points? Sure. And now here's how I want, it says where are they located? So I don't want the ordered pair. I don't want the coordinates of this point. I want just the x. When it says where are they located, we want the x value. I don't care about what the y value is. Okay, so the local max and min, did it say max and min? And max or min? On F, right. So at x equals 1/4. And again, you can trace, right? You can trace and put decimals, that'd be fine. So at 1/4, 3/4, 5/4, you guys see the pattern, right? This would be 7/4, 9/4, and that's 11/4, I believe. Isn't it? Right? Put the decimals too, fine. Just a list like that is fine. X equals. Where are they located? Okay? Where is it concave up? All right, now, what do we need to know? Where's it concave up? Is it concave up here? No, this is concave down until where? You suppose that's the inflection point? Remember the inflection points where it switches concavity? Well, sine does have nice symmetry. So it turns out that the inflection point is right there in the middle, right? Right there in the middle. So it's going to switch. So this part's going to be concave up here. This part's going to be concave up here. And this part's going to be concave up here. So what is this point? 1/2 to 1. So from 1/2 to 1 is going to be concave up. And from, what's that, 1 1/2? So 3/2 to 2, it's going to be concave up. And from 5/2 to 3, or 2 1/2 to 3. Right? Concave up. Concave up. Okay? Good question, because this is important discussion. Does it have any inflection points? Well, yeah, we had it's kind of backwards. We kind of had to find those first, didn't we? That's an inflection point. That's an inflection point. These are all inflection points right there. That's where the concavity is switching. Concave down, switch to concave up. Switch to concave down, switch to concave up. Switch to concave down, switch to concave up. Now, I wouldn't include, usually on a deal like that, I wouldn't include the endpoints. This would be one back here at 0. That would be one at 3. If you put those or didn't put those. Because usually because you need to be able to look on both sides, right? To tell that it's switching from concave up to concave down. And since we're only starting there, I usually wouldn't include it. But if you did, it'd be okay. Okay, so 1/2 at 1, 1 1/2, 2, 2 1/2. Right? But if you want to include 0 and 3, you could. I don't know, anybody looking up in the back? They it was an even. In here, they got a mistake. Is this 18? They got a mistake here. They only have 1/2, 3 halves, and 5 halves, which are the places where it's switched, which is those. But these are inflection points too, right? For sure, right? Concavity's changing there, right? So they missed those. So, and there are some mistakes in this book, but that's definitely one right there. Okay, and then what's the other one? Any roots? Where are the roots? Those are they're the same inflection points. Where's it crossing its axis? Okay. So good. Just being able to talk about these different points. Is the function a periodic? What's its period? 1. It repeats. It starts here, goes through one whole cycle at 1, goes again at 1. Right? We already knew that, but if you hadn't remembered that and just graphed it, and could go through there, you could trace and you could see where that was at. Is it an even or odd function? Switch back to your menu 4 or 5. Menu 4 or 5. Or is it 5-4? Menu 4 or 5. Menu 4 or 5. Go back to a standard window. Okay? What's that look like? It's odd, isn't it? Odd goes through the origin. Odd has origin symmetry. Odd has origin symmetry. So you go this way and up, this way and down, right? Opposites. You get opposites in, opposites out. It's an odd function. Okay? Odd function. Even would be like cosine, y-axis symmetry. Okay? So we had some of that stuff. All right. What else? Any other homework questions? Don't be shy. We don't always have this much time. 7, E, and F. Polynomial, yeah, the absolute value in there makes that kind of interesting. So you can't really use your calculator much here. We got this function q. Now, when you see q of x, think y values, right? Y, yeah, it's a function, but think q of x represented for y values, right? That's what we think here when we're looking at this. Now, it's a degree 6, which we said that means it's going to be an x to the 6, right? So it could have how many humps? Could have 5 humps. 1, 2, 3, 4, 5. Tails have to go in the same direction when it's an even power, right? If it's an odd power, they go opposite directions. So we could have as many as 5 humps, but it could just be like that too. It could just do that. Or it could have that many humps, right? I mean, but the most it could have is 5, and the tails do have to go in the same direction, okay? So it asks you about roots and stuff like that. So is it possible that q is less than or equal to 11 all the time? Now that's where it's really important to think of that as y values. What they're asking is it possible that all the y values are below 11? Sure. Here's 11. It could be make sure I didn't have too many of them. It could be like that, right? All the y values would be less than or equal to 11. So that's very possible. And, it says justify your answer. That picture would do it, right? That picture would be a great justification for them. Okay? Is it possible that the absolute value is less than or equal to 11? Why not?
Because those tails are going to go together, the y's just going to.
Okay, so, but let's back up a minute. So what does this mean then?
They have to be positive.
Well, no. That means whatever you put into there will turn to positive.
So those negative y's.
So all of these negative y's down here that are down at like negative 20 are actually going to be positive 20, right? And so if you put negative 20 down here where your y's are negative 20, they'll turn to positive 20. Is that less than or equal to 11? No, right? So the answer to this is no. Now here's another.
Could you put a negative sign outside the absolute values?
Well, yeah, but then you'd be changing the problem. I'm not sure what you mean by. I mean, if I just did that, then that's a different problem than this. You know what I mean? Here's a good way to think about this, though, guys. Is another way of this is saying this right here. That's what that's saying. That's saying, is it possible that the y's are between negative 11 and 11? Right? That's what's really happening. And they can't be, because the tails have to go on forever, one way or the other. Here's another way to think about it. When you have a graph and you put bars around it, what does it do to that graph? When you have a graph and you put bars around it, what does it do? This is where what you said is right. It makes all the negatives positive. So if I ask you to draw the graph of the absolute value of Q, the Q I have here, all of these pieces that are negative would flip up here and be positive. This would be the picture of Q. Does that make sense? With bars around it? Now, is it possible that that stays less than or equal to 11? No, because these are going to keep going, right? In other words, I mean, do that. Let's do that. Let's do it. Let's do a couple of them on our calculator. This is good. So let's put in x squared minus 4. Okay. All right. Now, everybody get a good look at that graph. Okay. Now let's go back, tab, and go back up there, and now go in front of that and type ABS. No, in front of the x squared, right there. Type ABS, left parenthesis. Okay, that's how you do absolute value. Now you can find that actually. You can do bars. It's not this vertical bar here. I can't remember where it is. It's I think it's over here. Go to this button right here, Will. Huh? No. Just hit this button right here. That you can get the absolute value bars there too. Okay, under that. But hit escape. But you can just type ABS. Hit enter. See what happened there? See? That's the absolute value of x squared minus 4. All that happened is the part that was negative, boom, is flipped up. Became positive. So it's really easy to do absolute value graphs. You just graph the thing that's on the inside, and then just take whatever was negative and flips up. So that helps you to understand why absolute value x is a V graph. Because all that is the graph of y equals x, and you just take this part that's negative and boom, flip it up. Right? That's why it's a V graph. Right? So it works for any graph. So it's kind of cool. So we can do that. Right? Yeah, x to the 6 minus 4. There you go. Do the absolute value. Now, it looks like it doesn't touch, but it actually does. That's just a little bit of limitation of the calculator. Right? So, yeah, do like plus x to the 5th. Go in there. What do you do? Right there. Go plus x to the 5th. And then, no. And then minus 6x. Let's see if that gives us a few humps and bumps. A little bit. Kind of hard to see. But that's all the bars really do. So that's another way you could have thought about that one or asked about that. All right. What else? 26. Find the natural domain and range of each of these. Express your answers using interval notation. Okay? All right. So, again, you could go to your calculator. Now, it will be good to know that e to, well, that's a nice graph. Nice axis. It would be good to know that e to the negative x, that's 1 right there, is just this graph right here. But, we'll go ahead and graph it for us, but if it's small, you will be able to have it, but it would be good to know this. Okay? So what is the natural, don't be fooled by the term natural domain, just what's the domain? I mean, natural domain is just, without me telling you any different, what's the domain, what is the domain of this graph? Well, what do you got? That's a good way, that's a good way to say all reals. If you want to say all reals, that's fine. Remember, what domain is I usually think of it in the negative. Are there any x's I can't put in? Are there any x's like that one problem? We can't put in a 3, we can't put in a -3. Okay, so the domain is everything but those. Okay, are there any x's I can't put in here? No. The x's, I can put in x's, because this looks like this never goes straight up. It's going to keep going. So if I came way out here, I'd get a value, it'd be way up there. But, right? So negative infinity to infinity. So there's no asymptote here that it's stopping at, right, on e to the x. And then what's its range? They want the range too. Now, okay, it did say interval notation. I'm not going to say that, right? If I said the domain and you said all reals, that'd be fine. But since it did say interval notation, yeah, maybe we should have put that. Right? And what's the range? So, right. So now if you put y greater than 0, and you can use y anytime it's a range question, you can use x anytime it's a domain question, even if the function is in t's or something else, right? I'd be okay with it. But probably better to say 0 to infinity. I think it's good to get in that half, right? Which is the same as saying greater than 0, right? That 0 to infinity would be good. That's what that is. Okay? But again, graphs are the best way to look at domain and range. You see a graph, it's just easier to see. Since you're going to have your calculators, you'll be able to do that. Okay? Even function or odd function? Or neither? Neither, right? Most graphs are neither, right? Periodic? No. Why? It doesn't repeat. There's no period where it repeats. Okay. Any roots? Any local max or min? Any inflection points? What's an inflection point? Changes concavity. What's this graph? Concave up all the time. Yeah, so e to the x is pretty boring if we want to talk about maxes and mins. And, it's always decreasing. This particular one's always decreasing, right? Okay. So, doesn't have a lot of stuff going on as far as that. Sine curve was a whole different story, right? Inflection points all over the place, concavity changes, local maxes, local mins, a lot of stuff going on. Anything else? Let's talk about the quiz. We've done a lot of review, really, as you think about what we've been doing here. Section 1.1, domain, range, piecewise. Don't forget about a circle, x minus h quantity squared plus y minus k quantity squared equals r squared. Excuse me here a second. All right, so now to practice a piecewise, you can just make it up. You can just make one up. Say, okay, I'm gonna do a half circle that's centered right there. That's got a radius of 3, and so that goes 1, 2, 3. I go 1, 2, 3, and so I could say, okay, I got a circle that's there, and then I'm gonna have a graph. I'm gonna have a line that goes there, and then maybe I'll skip and have a little gap here, and then I'll have an open circle. And then I'll go down 3 over 2, down 3 over 2, and I'll make myself a line. Boom, I got a piecewise function. Now, let me find the equation of that, right? Just make them up, make one up, right? And practice that, okay? And find the equation of that. It'll only have part circles and lines. That's all I'm going to have you do. Okay, so you can practice that on your own. But you're going to have to do that. Write the piecewise definition out. We had number 12 in our homework was about that, right? And so you can go back and look that one over, but you can practice some on your own, right? Practice some on your own. I do not have a set of problems today that's like, here, do these, and that's review for the quiz. Sometimes we do. Sometimes we have some review kind of things that we can do, and sometimes it's just, hey, here's your homework. This is what you've been doing. Now you got to show me you can do it. Okay? Those were the big things out of 1.1. But go back and look at those homework problems. Okay, 1.2 is mostly about graphs. That's when we got into even, we got into odd, we got into periodic. Were the big things there. I'm trying to think what the homework was about. We had, shifts, geez, that was a big part. Transformation, stretching, right? Stretching, shrinking, shifting, flipping, describing that, maybe sketching it. We talked about asymptotes more in this one. So that was a big one. Be able to use your calculator. We didn't use a calculator so much on that one. But then also and I've talked a lot about this, is just looking at a graph and saying something about it, like the volume of that hemisphere, and we had those graphs, as it filled up, what did the graph look like? And be able to just read units off of a graph and know what it's talking about and so forth, okay?
So how do you find, like, the period of, like, if it gives you a function?
If you look at a graph, probably looking at a graph.
Graph it?
Yeah, you would graph it. If it gives you a function, you want to know if it's periodic or not. You're going to graph it and look at it and see, like right here, is it periodic? Well, it's got to repeat, right? It doesn't mean it's got to be a sine graph, but it's got to repeat. I think in your book, there was an example. If you look at page 20, right? If you turn back to page 20 in your book, there's a couple of them, a couple of periodic functions there. One looks like just kind of a basic sine graph, right? The other one is got some other weird kind of things going on there. But that's periodic, okay? Tangent is periodic. And it looks more like, it's got this, I missed that one. And then it's got this, right? And it's got this, right? And it repeats that same piece of the graph every pi units, you get those values over and over. And I usually do this, okay, that value, if I go over pi, do I get that value again? I go over pi, do I get that value again? Does that work for every value? I go over pi, I get that, over pi, I get that, right? It's repeat, right? So pretty easy to notice, and if it's not, look over on page 21 then, look at question 28 there, that graph right there. Is that periodic? Well, you can't see enough of it, so you can't see enough to tell, so you'd have to graph in a big enough window to be able to see. But that's a pretty obvious one, really. Just it repeats. Okay, 1.3 then was function families. And to be honest, there's nothing really new there. All that section 1.3 allowed us to do, was take all the stuff we learned over here and talk about it with these different functions. So look at our questions today, right? What were the questions about? The questions were about shifting. The questions were about periodic, even odd, domain range, right? That kind of stuff. So we were just talking about those things we've been doing in the first two sections with this group of functions. Now, we learned a lot of different things about these functions, what exponentials look like, what logs look like, what trig ones look like, what asymptote kind of functions look like, polynomials with their tails going every which way. But you'll have calculators tomorrow. So if you don't have that all memorized, what one of those looks like, you'll have your calculator to be able to draw a graph and look at it if you have to. Okay? So, you got that. Okay? That's it. That's it. The quiz, it's going to be straightforward. It's going to be right there with function notation and understanding what it's saying. And doesn't mean it's easy all the time. There's going to be some problems that are going to stretch your use of that notation and make you think about it in maybe a different way. But that's always part of it. That's always going to be part of the quizzes. There's going to be, the expectation, I think, for you should be, there's going to be questions on a quiz that are going to seem very familiar, much like the homework was, things we've talked about, and then there may be some questions that just make you look at it in a little different way, or that kind of are testing how deep is your knowledge of this, right? Can you just mimic the homework problems that we did? Or do you understand it in such a way that you can answer a question that's a little different and uses it a little differently than what we did? And I think both of those things are important. Okay? That second one's kind of hard to study for, right? There's not a lot you can do. That's an ongoing thing. That's an ongoing paying attention, spending time in your homework, asking questions. Like I said the other day, be honest with yourself. Do I really understand this concept that we're talking about here? And you'll get more comfortable with that as you go along. But there's probably a certain element on any of the quizzes that will probably stretch you or test you in that way. There's just not a lot you can do to be ready for it, other than to just work hard at it every day. Ask questions, and make sure you're understanding what's happening. Okay? All right. So, let me see. I was going to do one other thing with periodic. So we talked about that. So looking at a graph, telling if it's periodic, does it repeat, that part of it's pretty easy. But we also have those questions. So if I've got a period if I've got a graph whose period is 3/8, let's say, and I tell you that f of 1 equals 2, right? What's another value you could tell me? You could tell me f of 1 3/8. Now, what's the best way to deal with fractions? Now, you have a calculator, so that will be helpful. But I'll be honest, I like to think in terms of improper, and because I'll think of it this way. I'll think of 1 as 8, and maybe this is my trig background, right? I like to think of pi, if I'm doing pi 6, 2 pi 6, 3 pi 6, I like to think of pi as 6 pi 6, right? I like to think of it in those terms, and that helps me. So I like to think of that as 8/8. So I would probably do this. But 1 3/8 is fine. You can do 1 3/8, I don't care. So that would be 2. And what else would be 2? 14/8, right? I keep adding 3/8. I don't even care if you reduce that, doesn't matter. That would be 2, and so forth and so on, right? And by definition, this would be saying f of x is equal to f of x plus or minus 3/8, right? That's the definition of periodic, right? If you shift it 3/8, you get the same output as if you didn't shift it.
Are the lines periodic? Like, it's just the same thing over and over and over?
Well, it's the same slope. It's not the same.
Well, I mean, if you have like a flat, like y equals.
Oh, you mean horizontal line?
Yeah.
Oh, a horizontal line. Is a horizontal line periodic?
Like y equals 2.
What would be the period?
I mean,
Yeah, that's what I mean. It doesn't have a specific value for its period. It certainly repeats the same output all the time. Yeah, I was going to say, we probably get a discussion about that online that would be yes or no. You could say f of x would equal f of x plus p for all values of p, right? I mean, so it's periodic with a period of anything, but I don't know that would be. That's
well, I mean, if you're given like a function and a period would be wrong, you assume that could be a line.
Yes. Yeah, that's a whole different question. That's like saying, because if I give you this, then you're picking out a very specific function that would fit that, but there could be other functions that would fit it. So yes, it'd be wrong to assume, okay, all the values are 2. Yeah, because then you're making an assumption on information that's not there. You see what I mean? So yes, that would be wrong to do that. Okay? Because what you'd be getting into is it could be, f of 7 could be 2, that's true, right? And we talked about that with a sine graph. I mean, what about f of 1 1/8? So if I ask you, could f of 1 1/8 be 2? Could be. Does it have to be? No, see, that would get back to what you're saying. Yeah, just because all these values that are one period away have to be 2 since it's a periodic function. That doesn't mean there's not some other values that are 2. And we did that with sine graph, right? Here's a sine graph. The period's 2 pi, right? Oh, that's awful. Period's 2 pi. So every 2 pi, it's going to repeat this 0. But it also has 0 here and here and here and here, right? But they're not part of this repeating process, right? Because you're right, here you get 0 every pi unit. So you say, hey, the period might be pi. But then you go to this peak and you say, wait a minute, every pi units I don't get that value, right? So there could be some extras in there, right? Okay, so that, I mean, to me, that is it for the quiz, other than you just kind of practicing those things, looking back at the homework, asking me individually if there's part of this homework we haven't really went over that you want to talk about. What I wanted to do here just real quick was, and I want to give you some work time on either studying for the quiz, or maybe you can do that outside of class, unless you have some specific questions. I wanted to just do some stuff with trig equations. Now, I've got an IXL here, and I've also got a worksheet. Now, I'm not going to pick these. They don't have to be due tomorrow. Your first priority study for the quiz, but you should do them, and I'm probably going to make them due. I'll probably make those due on, let's see, what's tomorrow, Thursday? I'll probably make those due on Friday, okay? And then we'll work on them. You can work on them after the quiz. And then I'm going to have another kind of longer-term assignment that's due on Monday. But then on Friday, we're going to get started on some stuff, so you'll have an assignment there too. So if you can find time to get this done, maybe even tonight, it wouldn't be bad. You'd stay ahead of the game. But just solving some simple trig equations. So if I have sine of x equals 1/2, okay? What's the answer to that? Pi 6, right? Now, there's more to it than that, though, because sine, if you think of the sine graph, where does sine equal 1/2? Well, it equals 1/2 right there. That's pi 6, right? But it also equals 1/2 there. What's that? Go to the unit circle. Pi 6, sine equals 1/2. Isn't there also one right there? Which is 5 pi 6. Now, that would be good enough if I told you to only look from 0 to 2 pi, right? Then your answer of pi 6 and 5 pi 6 would be fine. Okay, so that goes back to knowing our reference angles, knowing the unit circle, practicing that. So we've talked about the trig a little bit, but we haven't practiced a lot of that. Now I want you to practice that and look at your triangles. Now, if you're looking at that and saying, geez, how did they get that? Go to triangles if you want. Say, okay, sine is the y value, or think SOHCAHTOA, opposite over hypotenuse. So this would have to be 1/2, 1, and this would be root 3 over 2. Well, that's a 30/60, right? 30/60. Well, 30 is across 1/2. Well, that's pi 6. So if you have to think of it that way, I don't care. However you have to think about it. But that's 30. There'd be another one over here. So that's, okay, pi 6. So pi 6 and 5 pi 6. But if I don't tell you that, and I think on this worksheet I'm going to give you, you're going to have some where they give you this, and then some where they don't. Then that's where you do the pi 6 plus, remember the 2 pi n? Because that would be this one, and then that would be all the way around again, and then again, and then again. Or you could go backwards, 2 pi, and the n could be negative, right? So that, and then you'd have 5 pi 6 plus 2 pi n, right? So if I don't give you the specific domain to only look from 0 to 2 pi, then you would do it that way. Right? So you got some of those to work on. Now, the other thing we can do with a trig equation sometimes is we do this. So maybe we do root 3, we do 2 cosine x plus root 3 equals 0. Solve the equation. Well, you do 2 cosine x equals negative root 3, then you divide by 2, cosine x equals negative root 3. Now, this is not on the quiz, guys. Right? This is not on the quiz. So we're done with the quiz review. We've done all that. That's going to be tomorrow. Get yourself ready, review, look at old homework, ask me questions, whatever you need to do. Okay, now, in addition now, what we're going to be working on, spending some time on this. So where does cosine equal negative root 3 over 2? Well, where's cosine negative? Over here, right? Because cosine is the x-coordinate on the unit circle. So it's over here. So negative root 3 over 2. Well, cosine is your adjacent over your hypotenuse, right? So it could be one of these two here. Well, what is that? That is, here's 1/2, here's -1/2, this is 1, 1. So what is that? Is that 30 again? Isn't that pi 6 again? As your reference angle? Pi 6. So what would this be? That would be 5 pi 6 and 7 pi 6. Right? I think I got those right, all right? Okay? So however you have to do it, whether it's drawing the triangles or it's, just knowing those values on the unit circle or whatever the case may be. Without a calculator now is what is the idea. That we can find these values without a calculator. Okay? There might be some factoring, you have to do whatever, but you solve these with cosine. All right, so you can have the rest of the time. Now, like I said, this is going to be, I'm going to give you an IXL here, and there's 8 little trig equations on this to do as well. And so this would actually be for Friday. Okay, so if you get out of the quiz early, you'd have some time on this tomorrow. I'll probably also assign another thing that will be for Monday. But so IXL, this is under the calculus section now on IXL, and it's C7, which is some solving like this. Try to get to 90 on that. And then C16, which is some graphing ones, some trig graphing things. Okay, so the worksheet and that is for Friday. Okay, all right. Rest of the time is yours. Ask questions, review for the quiz, whatever you want, whatever you need.